it means is that if you take any averages between two quantities or maybe more or whatever which are separated by a distance, then it does not depend if it is homogeneous in a particular direction, then what is the gap? It depends only on the gap, it does not depend on the origin. So which means if you measure something here or at some distance, then things are approximately the same thing in an average way is happening in the flow in that direction. In an average way, or that is what we say statistics means mean quantities, they don't change. Okay. Now, similar to that is the concept of stationarity, and this is very similar to the concept of steady flows in laminar flows. So, this is like steady flows in laminar case, or this is like the concept of homogeneous applied to time. Homogeneous was for space. If you apply the same thing to time, then what we get is this concept of what we call stationarity, and let me just write the definition. So, turbulence is stationary if statistical properties at n times. So, you are taking the observations at n time intervals. At n times, the statistical properties are invariant under the translation of time t1, t2, tn. And one particular outcome of this is that for stationary flows, let us say we are talking of mean of u, then mean of u will not depend on time. Because now when I say averages, if it's a first order average, then it's only the mean velocity or the mean temperature. Then if I take it at different times and if I say that this has to be just a function of the time interval, so then it will mean that it cannot depend on time. So this is the concept of stationary flow, and a lot of turbulent flows which we know, there the mean quantities do not change with time. So that is why we can use these concepts, and this in particular. So therefore, what will the if we apply the ergodic hypothesis on this concept, then what will we get? That will tell us that the time average will be equal to the ensemble average. That means instead of taking n different experiments, you take the data at you take time averages at with respect to time, and that will be the same, because the flow is in an average sense not changing with time. So ergodic hypothesis therefore in this case tells us that time average is equal to So now there are two ways you can take the time average. One is you have these realizations at different times. So you just take the average over a large number of times. Another way of doing this is, and which we define in a classical way, is the integral of the instantaneous quantity time as a function of time divided by the time interval over which the integral is taken. And actually, if you are doing discrete measurements, then the integral will also be in some sense an ensemble average only. You will make some approximations for in between ranges. Okay. So the time average we have defined that normally we take it as 1 over tau integral t to t plus tau of that quantity, and yeah, so that gives us the time average, and that will also be equal to ensemble average. Yes.
Sir, you told ensemble average is consisting of both space average and time average.
No. Actually, ensemble average is at each point and at each time you do the experiment n number of times and you take the average of that. That is what is termed as ensemble average. But if the flow is stationary, then instead of taking the time average, instead of taking the ensemble average, the time average will be equal to the ensemble average. Otherwise, actually, when you are calculating average, then if it's the ensemble average, it is ensemble average at each point and at a time. So you do the experiment 1000 number of times. So you measure the velocity at this point at after you start the flow at t is equal to 10 seconds, let's say. So that, and you do this for 1000 experiments, take their average. That is what will give you the ensemble average. So actually, ensemble average calculation practically is a very tedious thing, even numerically. Even if you do the DNS simulation, you have to run those simulations at least for a large number of times for the average to converge. You can't take an average over only 1 or 2 data. So actually, when we talk of average, we are meaning ensemble average. But because the flows are homogeneous and stationary, we can do with time averages or spatial averages. This is something which we have to be sort of very clear about.
So what is the translation of time mean?
T, that means if I calculate this average at t and t plus tau, the correlation which I take ui at t, uj at t plus tau, this is only a function of tau, not of t. That is what's meant by translation of time. That it depends only on the time gap. That would be if the flow is non-stationary. For stationary also it will depend only on the time gap. But if you go for the mean velocity, then mean velocity cannot depend on time.
Mean velocity will depend on time.
Will not depend on time for stationary flows. Then last concept which I want to talk about is isotropic flow. And once again, let's write the definition. If all statistical properties at a set of points x1 to xn at times t1 to tn, if these properties are invariant under arbitrary rotation of the axes of the coordinates. See, we defined isotropic as something which does not change with direction. So mathematically, for us to define isotropic would mean that they do not change if you change your direction of the coordinate axis. If it is kept as the If you rotate it in an arbitrary way, the quantities will not change. That would not be possible is right for a lot of quantities. But if you look at the turbulent fluctuation, so what you are saying, in fact, let me first come to that. So this is what I was saying. Suppose if I have a flow where there is a mean velocity u1, and let's say, so this is xi direction, this is this is the mean velocity u1, let's say. Now, if I claim if the flow is isotropic, then what will happen is, let's say I change xi star is equal to minus of xi. Now, in this again the mean velocity's direction is the same as before, u1. But in the new coordinate system, what is mean velocity? If earlier it was u1, now it will be minus of u1, because now the axis is pointing in the negative direction. So that means a flow with a mean velocity can never be isotropic. I think that is what you are probably trying to say. But this will not go with the fluctuations. And again we will talk of in an averaged way. The same just the instantaneous fluctuation, it will not be isotropic, but when we take averages of fluctuations, and it won't be the single average of the fluctuation will be 0, but there could be correlations, we will talk about that, and they could be, even in an isotropic sense, non-zero. So the doubt what you asked was very right, that there can be no mean velocity component in an isotropic flow, because anything which are with a vector sign will give a sense of direction, and that very much goes against the definition of isotropicity. Okay. Now, we will be later on coming into the course, so let's also give you some examples of second order moments. And here I will assume that we know what is a velocity fluctuation. So let's try to see, we want to find ui prime at x1 comma t1 times times uj prime at x2. This is a typical second order moment of velocity. Velocity fluctuation in the ith direction. So we take the velocity at x1 comma t1 and we find multiply it by uj. Now j may be same as I or it may be different as I. So I could be 1, j could be 1, I could be 1, j could be 2 and so on. So totally there will be 9 components. uj prime at x2 comma t2. So now these are general x1, x2, t1, t2. And when you take the average of this is a second order moment of the velocity fluctuation. Okay. Now, this second order moment, just going back in the same thing. So there are certain names which we have. There is something called now these are also called correlations. because you are taking the product and finding the average of this, then it's also termed as correlation. Longitudinal moment or longitudinal velocity correlation. This is the name given to if you have velocity in a particular direction and this is x, and you go to a point which is parallel to the velocity, and this is the position coordinate of this is x, position coordinate of the next point is x plus r, and if you now take a correlation of these two velocities, so r is now parallel to u, the distance is in the same direction as the velocity, then we say this is the longitudinal correlation. Okay. See, there could be many correlations. So this is just, so here what we have is this just a name, and just to make you familiar, r is familiar is parallel to u. Now this u is any vector, maybe I can call it as u prime. Now similar to this, there is another correlation which is termed as the transverse correlation, where what you do is you take u2 at x or u2 prime at x plus r. Now here the vector r is perpendicular to the component of velocity. So you are taking a correlation between two components of velocity and the separation is perpendicular. So then we call it as a transverse velocity correlation. Okay. So these may come in later in the course, right now they will not come in, but so this will be basically correlation of u2, let us say at x, y, z, let us assume it is a stationary flow, so time does not matter, times correlation of u2 prime at x plus r, y, z. So now u2 is in the two direction and the separation is in the x direction. So this particular correlation, when you take it, will be termed as the transverse correlation. Yeah.
So while taking the average of the multiplication of these two quantities,
Yeah.
what do we take it the average over? Like what variable are we integrating over?
So actually it's supposed to be the ensemble average. Okay, but if the flow is stationary, then you will do it over time, and if there is any homogeneous direction, you could do it over that direction. Okay. Otherwise they are supposed to be all ensemble, but if we were to do ensemble averages, we would never be able to proceed. So, and as most of the flows are stationary, so then time average provides us with a very nice way out. And then there could be a cross correlation or a cross moment. So this again, here you have u2 at x or u2 prime at x and times u1 prime at x plus r. So here you have one velocity in one direction, the other velocity in the other direction, and you take a cross correlation of these two. So then this is called as a, again you have to take an average. Now I will be coming to this term later, just soon in the lecture, but probably all of you know, or many of you have heard of, most of you would have done, what is Reynolds stress. Reynolds stress which you write is something, and we will come to this will be ui prime uj prime. So here in Reynolds, what I have talked about earlier are more complex concepts than Reynolds stress. Why? Because in Reynolds stress, they are at the same point. Ui and uj, you don't talk of any separations here. You talk of ui at the same point, uj prime at the same point, and take that average. So this is much simpler concept than what I have talked about earlier, but they may come in later, so that's why I just thought at least let me introduce those moments. In Reynolds stress, you are at the same point, you don't even, there is no separation. And this actually sometimes is also called the covariance, because you are at the same point, you are taking the variance of two quantities. So now with this, let's try to get to the concept of Reynolds stress and decomposition. We have, so we'll introduce this concept. So now first let's introduce some, let us look at averaging and some rules. Rules means you can, of course, averaging is defined as what? 1 over n sigma I is equal to 1 to n of that quantity. That is the meaning of averaging. So let's say we have a quantity, any instantaneous variable A, and if I take the average, so I will denote the average of A by angular bracket of A. And now what average is it? It actually is the ensemble, but could be time or spatial average over homogeneous direction. Okay. So now if there is a quantity B, so now there are variables A and B, or there could be more variables, whatever, and they could be scalar, they could be vectors. So A could be a scalar, A could be a vector. For example, A is temperature, then it is scalar. If A is a vector, it could be velocity. If it is a second order tensor, it could be stress. So any quantity we can take the average. Now the instantaneous A, we will write it as at any time is equal to A plus A prime, or I could even use capital A prime. So at any instant, A is written as the mean of A, and whatever is the extra amount at that time or at that for that instant or for that realization, this over and above the average, we call it as the fluctuation. Okay. Now here the difference in notation comes. Lumley's book uses capital A. Lumley uses A with a hat for instantaneous quantities, and instead of angled bracket just uses capital A as the average and uses small a as the instantaneous. There is no prime. Pope's book uses this notation, but Pope's book does not use the prime. I have decided to use the prime because when I do things in the class, sometimes the capital U and small u become confusing. So that is why, at least in the notes, I will use this. So just be clear about this. So in Lumley's text, this is written as A hat, and this is written as A, and this is written as small a. And in Pope's book, this is written as A, the mean is written as capital A, and this is small a. Okay. So let's not get now some of the rules. So A and B are so there are three things. If you now realize, there is instantaneous, there is a mean, and there is a fluctuation. Okay. Instantaneous is the total variable, and this is equal to sum of mean plus fluctuation. So now anything without a prime or without an angular bracket is an instantaneous quantity. Now here what I am saying is, what will be mean of A plus B in terms of mean of A and mean of B? If we use the definition, mean of A is equal to 1 over n sigma I going from 1 to n of A and plus this. Now the summation, these two summations I can write separately also, the answer will not change. So therefore this mean of A plus B will be equal to mean of A plus mean of B. Okay. Similarly, mean of A minus B will again be equal to mean of A minus mean of B. And if we have a constant alpha, then mean of alpha times A will be equal to alpha times mean of A. Okay. Is this clear? Now, what will happen to, and then another thing which will happen is mean of A will be just the mean of A. If I take an average of the average, it will be equal to the average. Now, based on these, the derivative is nothing but a quantity at some time minus the quantity at a previous time divided by delta of this. So when you take the averages, the derivative operator and the mean, they can commute, because it consists of only summations and dividing and multiplying by scalars. So therefore, the time derivative of A will be this, and similarly partial A by partial xi will be equal to, of course this will require some sort of a continuity of this function A. The function A has to be continuous and differentiable and all that for this to happen, but the average, the mean operation and the derivative, they commute. What's the meaning of commuting? The order is not, order can be changed. A plus B is equal to B plus A. That is the commutative law of addition, the first law which you do in school. So they can commute. Now one thing which I have missed out is what is, now based on this, for any quantity, what is the mean of A prime? This will be 0. And this we can get from the expression that A is equal to mean of A plus A prime. So let's take the mean of this. So we will get mean of A is equal to mean of A plus mean of A prime, and this means mean of A is equal to mean of A plus mean of A prime, and this implies mean of A prime is equal to 0. Okay. Now what will be is this average of A times B. Will this be equal to average of A times average of B, or can it be different? And for that, what do we do? Let's do the same thing. Let's write it as A can be written as mean of A plus A prime times B. B is mean of B plus B prime, and take an average. So this becomes equal to, there's an average outside, then I get, there's an average outside, and then what I get is, the first term is average of AB. Second term is average of A times B prime. The third term is A prime times average of B, and the fourth term is A prime B prime, and then average of all these. So I've just expanded this. Okay. Now this will be equal to sum of all these averages. So average of AB plus average of A times B prime plus average of A prime times average of B times this plus average of A prime B prime. I have just written the sum of averages as all the 4 averages separately. Now, what happens to the second and the third term? In the second term, this average of A can be pulled out. Okay, because this is like a scalar or like a constant quantity. So once we pull it out, so this second term becomes equal to, so this becomes equal to, now the first term becomes just average of A times average of B. The second term becomes equal to average of A times average of B prime. The third term becomes average of A prime times average of B plus A prime B prime. And average of B prime is 0 and average of A prime is 0. So therefore these two terms will become 0. Okay? Fluctuating quantities have 0 averages. So therefore this becomes equal to average of A, average of B plus average of A prime B prime. Okay? And will this average of A prime B prime be 0 or will it not be 0? It depends if they are related or not. But in general, it will not be 0. And let me give you an example. First of all, if you look at the case, if I look at average of A prime times A prime, then average of A prime square will never be 0, because A prime is a fluctuating quantity, but if you multiply it by itself, whenever it is positive, it will be positive. Whenever it is negative, again average of A prime or A prime square by itself will be positive, negative into negative. So together when you do A prime square, it will never be negative, it will never be 0. So that is one thing. And then for the second thing which was said just now, suppose let's have a look at this variables, and let us look at variables which are correlated variables or not. Suppose if I have a quantity A prime which is random, but I am just making something up. So this is suppose A prime. So by itself A prime will have a 0 mean, as you can see. It is fluctuating about this 0 line, it has a 0 mean. But, and if I have a quantity B prime which and if there is a third variable C prime which goes like, let us say, I've just made some random this thing. Now, if you look at these three variables, if I look at the product of A prime times B prime, by itself mean of B prime is 0. But whenever A prime is positive, by and large B prime is also positive at those times. And when A prime is negative, B prime is by and large negative. May not be always, but if that's what happens. So then what we say is A prime and B prime are correlated. But if we look at C prime is going like this. So when B prime is positive, here it is positive, but then there are instances when this is positive and C prime is negative. So maybe I may not have drawn a fully uncorrelated variable here, but that is so. In general, here if we look at these trends, so if you look at B prime times C prime, then when sometimes this is positive, sometimes this is negative, sometimes this is negative, this is positive, and it's a random mix. So then B prime and C prime seem to be uncorrelated. And similarly, A prime and C prime seem to be uncorrelated, but A prime and B prime are correlated and their average clearly will not be 0. Okay. So in this example, So in this example, what we have is A prime and B prime, they seem to be correlated, and this we can see average of A prime B prime is greater than 0, but average of A prime C prime is equal to average of B prime C prime is equal to 0. So from here what we can say is A prime and C prime are uncorrelated. And the measure of the degree of correlation, this one uses how do we find the measure of the degree of correlation? And for that what we do is we say if it goes from -1 to 1. So what we will do is A prime square we know will always be 1, and similarly B prime square, A prime by itself will be 1. So therefore what we do is we divide this by equal to, it will not be 1, it will be A prime square will have some value, it will be positive, it's not 1. So because A and B can have any values, so A prime square will always be positive, B prime square will be always positive, and they are perfectly correlated, the variable. So we divide this by mean of A prime square and mean of B prime square, and to make it non-dimensional we take the square root. So this is what is termed as the correlation coefficient between A and B, and this gives for any two variables whatever be their dimensions, when you take it out and because you divide it by their individual values, so it always gives you some sort of a coefficient which will always be between -1 and 1, because A prime by itself cannot exceed A prime square and similarly B prime. So if they are -1, then there is a totally negative correlation, they are not uncorrelated. If it is +1, they are correlated. That means as B prime increases, A prime, both of them will be positive at all the times, and so on. So this is the meaning of correlation. Okay. So now given this, let's now come to the Navier Stokes equations and their averaging. So this is again we have learned the rules of averaging, and we have seen what are these correlated variables, because the major variable which we will come to, which we call as the Reynolds stress, will be a correlation which will be a variance of covariance of U prime and V prime or whatever, two velocity components. So, now we will go to the Navier Stokes equations, and we are looking at the simple incompressible form. So, the instantaneous equations, or the what we call as the equations, these are partial ui by partial t plus I wrote the same equation in the last class, but there I deliberately used j as the free index. Now I am using I as the free index so that you are familiar, you should be able to understand this. Whenever you look at the equation, first thing you should look is how many, is it a scalar equation, is it a vector equation, is it a tensor equation. So then we realize just one term is enough to tell us this. We look, there is only one index here. So I should be the free index in all these. So if there is any summation, we use any other index, j, k, l. So we use j for summing, and here we have dxj, dxj. So this is the Navier Stokes equation for incompressible flow, and then we have the continuity equation. These are our governing equations. Yeah, any question? है तो पूछ लो कोई. Okay, so these are our governing equations, and then what we do is we take mean of these. Now before taking mean, what I am going to do is I will also write it in other, using the continuity equation, I will write it as so what I have done is I have taken the uj inside here, and that is because of the continuity equation. If I expand this, so then what will be the full form? dui by dxj uj plus ui duj by dxj, which is 0. So I get to this form again. Okay, so this we can do, and now when I take the mean, so what will happen to the first term? So we will write ui is equal to mean of ui plus ui prime, fluctuation. So now when I take the mean of this equation, what I get is partial see here I have already shown you mean of A times B is equal to mean of A times mean of B plus mean of A prime B prime. So I have used that fact here. So therefore this mean d by dxj is as it is, it becomes d by dxj of mean of ui times mean of uj, and the second term which is ui prime uj prime, I just get a d by dxj of that. Okay, so all that we have done, and this is what we are left with. Okay, so is that clear? Agar if there are any doubts you can ask. Now one thing we realize is whichever are the linear terms, they come out exactly as the same form in the linear way. Because in the linear term it becomes mean plus fluctuation, and fluctuations are 0. See, we have also used the fact that partial, when we take this, that the average of the fluctuation is 0. That has been used. Otherwise we wouldn't get the, actually this becomes partial mean of ui by partial t plus partial ui prime by partial t and mean of that. So mean of that becomes 0. So all the linear terms just translate as it is with a mean term. It is in the non-linear term that we get these correlations. Okay? So yeah.
इसमें अगर सब्स्टिट्यूट करें जैसे ui को मीन ऑफ ui प्लस ui प्राइम,
हाँ वही तो किया है हमने.
हाँ तो फिर इसमें एक और टर्म ऐसे और टर्म आनी चाहिए ना कि लाइक ui प्राइम इनटू मीन ऑफ uj, इस टाइप की टर्म्स नहीं आती.
नहीं, वो मैंने पहले भी दिखाया था जब हम ए बी का मीन लेते हैं. सी दिस साइड, तो उसमें ये व्हाट आई थिंक व्हाट यू आर टॉकिंग ऑफ आर दीज टू टर्म्स, मीन ऑफ ए टाइम्स मीन ऑफ बी प्राइम and mean of a prime times mean of b, which becomes 0 because mean of b prime is 0 and mean of a prime is 0. Okay. So this is what we get. And now what does the continuity equation give us? The mean continuity equation. This will become partial ui by partial xi is equal to 0 or partial, I can write it as uj by partial xj, anything, it's the same index, so write it like this. This is what the continuity equation is. Okay. And now using this, what I can do is I can pull this mean of uj out of the derivative also because of continuity. So I had done that earlier, put it inside. Now in this mean term I will pull it outside. So when I pull it outside, this equation becomes partial ui by partial t. Now I will not be very particular about putting the hat or not on u, because capital U is capital U, the fluctuations are primes. So if it is any capital U, I'll not bother so much about the hats, which I was very particular in the earlier first lectures. But now that's why I decided to use the prime, so that there will be no confusion. So yeah.
So this assumption del u by del xi, you've used this before also, right? Del u by del xi.
No, that was this one.
This is the mean.
This is the mean of that, yeah.
Yeah. So when we were doing that assumption there.
No, that was not an assumption. It's a continuity equation for incompressible flow.
And how?
So I take, what I have done is, I have taken, write this ui as ui, mean of ui plus fluctuation of ui. So now the fluctuation of ui, I can take the derivative outside. So it becomes d by dxi of mean of ui prime. So that has to be 0.
But that we are already known, right? Because del ui by del xi equal to 0 means that del ui. Oh, okay.
So this is for the instantaneous, but the continuity equation, and again this follows from the fact that linear terms get the same form in the averaged form. So what it also tells you is that the fluctuating velocity also is divergence free. See now from here, if I have to get the equation for fluctuating velocity, how will I get it? Tell me.
So you could subtract this from the normal Navier Stokes that we had.
हाँ नहीं, नॉर्मल नेवियर स्टोक्स ये है, एक मेरे पास मीन वेलोसिटी इक्वेशन है. If I need we need to subtract the two equations. So that will give me an equation for the fluctuating velocity. If I need, and the fluctuating velocity equation, I cannot make simplifications, because that velocity changes with time and space, everything. So if I need an equation for the fluctuating velocity, I will take this equation and subtract the mean equation. Okay, so that will give partial ui prime by partial t plus something something whatever I get, and we'll do that also, but not now, maybe So that's why you have to be very well versed with these. So now what I was saying was, if I write the equation, I can write it in this form: plus mean of uj partial ui by partial xj is equal to minus 1 over rho dp by dxi plus nu d2 ui by dxj, and then I put minus d by dxj of ui prime uj prime. What I have done is I have just played around with the equations. One thing is I have taken the uj out because of continuity equation and taken the second term on the other side.
So, this was my doubt, like for the third term that you have written on the RHS down.
Yeah.
There. So we know that with the two assumptions that you have taken, that for incompressible flows, del u I by del xi equal to 0, and then you took this continuity equation also, that del of mean ui by del xi is also equal to 0. If we had not taken this, we had only one equation there, continuity equation, which will give us del of mean minus, which would be equal to minus of del of fluctuations.
नहीं बट फिर हम मीन ले रहे हैं ना पूरे इक्वेशन का. एक मिनट रुको, आई एम नॉट, लेट्स सी, इज इट समवेयर इन दिस स्टेप और ऊपर, और सी दिस इज व्हेन आई टेक द मीन, this term becomes this, the first term, second term is okay with the, I have not used continuity anywhere, ठीक है, and to get this term also I have not used continuity. So this equation is without using the continuity. Continuity I am using just to pull this uj out. That is all what continuity is doing. The fluctuating term as such has not been, there is no continuity equation used to get this term or to simplify this. हाँ चलो, हाँ बताओ, आ जाओ बताओ, लेट्स गेट दिस क्लियर. हाँ ये इक्वेशन मैंने लिखा था, बट आई हैव नॉट, दिस इज ये अंदर, हाँ ये तो, हाँ. सो दिस इक्वेशन इज वैलिड फॉर मीन एज वेल एज द इंस्टेंटेनियस. Okay, so I can use it on the instantaneous to pull this inside, and once I get my equation, then I use it on the mean to pull the uj out.
So, but our stationary flow condition
This-
should only be valid.
This is not stationary, this is continuity.
Yeah, I mean, but if we take an ideal situation, then this should only be valid on the mean, right?
No.
The mean of ui
No.
would not depend on xi.
No, this is not, see, it's not xi, it's a summation. So this is a mass balance equation. See this term, I think now I get your confusion problem. See this term dui by dxi is not saying that gradient of u is 0. What it is saying is divergence of u is 0. So this comes from mass balance. If density is constant, then what you get is, for instantaneous flow, partial u1 by partial x1 plus partial u2 by partial x2 plus partial u3 by partial x3 is 0. So this is a consequence of mass balance, not a consequence of anything else. Okay? So this is, it's not the gradient. So then, and the reason why I am pulling this out is, now when you look at the mean velocity equation, what do we find? The left hand side is exactly the same as the instantaneous equation with mean velocity being replaced. On the right hand side again I have the same thing, but there is an extra term. So now let's maybe we'll talk about it today, or so now what this tells us is the mean velocity equation. Let me make some observations. Same as instantaneous equation, but with an extra term on the right hand side. Okay. Now, this minus 1 over rho dp by dxi plus nu times d2 of ui by dxj, this is nothing but equal to now this part what I am writing, if I write the total stress tensor as minus p times delta ij plus mu times dui by dxj plus duj by dxi. Now, this part which I am writing here, this is the constitutive equation for a Newtonian fluid, that mu times dui by dxj plus duj by dxi is equal to the viscous stresses, and to that we add the pressure part or the normal stresses, that gives us the total stress. And what we find is that on the right hand side, what we get in the average equation other than the third term is basically nothing but the average of the stress tensor, which is fine because that is what we have done in the equation. On the right hand side, we had a pressure term and the viscous stress, together we call them as a total stress tensor, and we take the mean of it. They are all linear terms, so we just get the mean of sigma ij. Okay. So, but then what we have is there is an extra term ui uj or ui prime uj prime, and this extra term which we have, so what we can do is we can write the averaged equation as dui by dt plus mean of uj dui by dxj is equal to 1 over rho d by dxj of mean of sigma ij minus rho times mean of ui prime uj prime. Let me write this right hand side again. 1 over rho d by dxj bracket open sigma ij minus rho times अब एक बार ये मैंने दोबारा I have written it again, so therefore I will erase this part. And this is what we get, and what we see is that the mean equation is almost the same with this extra term, and this extra term is what we call as Reynolds stress. Now, in the next class what I am going to do is I will talk a bit more about the number of equations and number of unknowns. Okay? And I will give the physical interpretation of Reynolds stress, and then we will continue from here. But this is how Reynolds stress appear in these equations, and they appear because of which term? Because of the non-linear term. If the equations were linear, Reynolds stress would not have come. And so it is this non-linearity which causes, which is the reason for the flows, for the turbulence to show up in the equations, and otherwise the mean equations and they would be have the same form. Okay? Yeah.
Would that be